Good evening, gentlemen. While I'm still waiting for files to copy off of those old disk drives, let's talk about memory cards for TRS-80 Model IIs. By the way, if you're watching this video on YouTube, please make sure that you're running an ad blocker. I'd rather Google not get any ad revenue from my content, even by proxy. And if you are into such things, you can check the links down in the video description if you would rather consume my content on all tech platforms. This is the stock 64K memory card for the Model II. This is all the RAM. They are 16K by 1-bit RAMs, so to get 64K it takes 4 banks of 8. All of this shit over here is mostly for the refresh logic. This is dynamic RAM, so whatever's stored in it fades over time, and there has to be logic elsewhere on the board to periodically refresh the contents of the RAM. It's quite complicated, but the reason that they did that was it's still the case today too. Dynamic RAM like this that requires the refresh is much cheaper than static RAM, which does not require refresh per unit of storage. Nowadays, however, you can get like 512K by 8 static RAM chips for like $5 a piece. So for old computer hardware like this, there isn't really any compelling reason not to go with static RAM when we're building our own cards, unless we're making exact reproductions of historical boards, which isn't the case with this project. A little bit of this logic does some decoding, memory address decoding, page decoding I should say, so that it knows when this is the particular RAM board that's being accessed, and when it's a different RAM board if you have more than one installed in the machine. So anyway, yeah, that's the stock board. Lots of chips. I propose though that we can replace the entire board with these 4 chips right here, and in addition it'll give us a whole 512K of RAM, which is the maximum that the Z80 side of the big Tandies can handle, with only 4 integrated circuits, unless I'm really missing something. So let me present these ideas to you, and then maybe you can tell me if I'm maybe full of shit. But first, we should probably enjoy an adult beverage because it's been a shitty day. I don't know. I don't like talking about that kind of stuff like we were talking about before. It always alienates people, and seldom comforts people who don't already agree with you. You know what I'm saying? So it's not good to talk about that kind of stuff from an interpersonal standpoint. Sorry, guys. Anyway, I digress. Let's get back to this. Before we talk about this, though, let's talk about the Z80 CPU a little bit, so that we can get everybody here on the same page before we start talking about how to maybe implement this RAM expansion for the Model II. So the Z80 is an 8-bit CPU with a 16-bit address bus, which is very typical for the 8-bit CPUs of the era. So with an 8-bit data bus, we can store any value between 0 and 255 in a single memory location. 8 bits will give you 256 possible numbers, the first one being 0, so the last one being 255 rather than 256. And with 16 address lines, we have 65,536, i.e. 64K, possible locations that we can store those 8 bits in the CPU's memory space, right? But wait. Didn't we say just a little while ago that the Model 2 can address 512K of RAM? How does this work, being that the Z80 CPU itself can only address 64K of RAM? How does this work? Well, it uses a banking scheme to do that. In the technical manual, they call them pages, but most other documents that talk about these concepts will call it banking. In Tandy's Model 2 technical manual, they refer to banks of RAM as all of the RAM on a particular card, and pages as, like, since this is, the memory map's divided into 32K pages on the Model 2, so this 64K card would have 2 pages of RAM on it, and using the jumpers you can configure where in the memory paging scheme those two pages go, but the card is one bank of RAM according to the Tandy book. And that language is a little bit different than most of the other documentation that you'll read on the subject. So I'm going to continue to call them pages for the purposes of this video, but you may see them referred to as banks sometimes, so don't get confused. Anyway, the Z80 CPU's memory map, let's look at it like this. Here is all of the memory from lowest values at 0000 up to the highest values. That's 16 bits. That's hexadecimal 0, 4 hexadecimal digits, up to FFFF hexadecimal. That's 16 bits, 4 hexadecimal digits. That's 64K of RAM. In the Model 2, it divides that RAM into two 32K pages. All right. Now this lower 32K page is called Bank 0, and the RAM, it's, for the moment I'm going to say that page 0 is always mapped into this lower 32K. That's not strictly true because at boot time a ROM gets mapped into, I think, the lower 4K. It may be the lower 2K down here, but as soon as the machine boots, the ROM turns off and we have the 32K page 0 down here. Okay, and the upper memory, this other 32K segment, is paged in and out depending on a value that's written to a 4-bit I/O port at I/O port location FF. We'll talk about that here in just a second. But basically, that 4-bit binary number that the CPU can write into that I/O port, that number can range from 0 to 15. So that's a total of 16 32K pages of RAM that can be mapped into this upper segment depending on the value of that I/O port. So if we write a 1 in here, which is the default configuration, then page 1 of our RAM gets mapped in here. We write a 2 in there, the next page gets mapped in there. So think of it as having, rather than 512K of RAM, you have 16 units of 32K each, which totals 512K, but you can only access 64K of that at a time. 32 of that K is always page 0, the lowest 32K of that RAM, and the upper part of it is what you can swap in and out. So if you want to move some data from, say, page 1 to page 2, you have to bank in page 1 in the top 32K segment, copy data out of that upper segment somewhere into this lower segment, then you bank in page 2 in this upper 32K segment, and you write those values back out of this segment somewhere into that segment again, which will write them into the other page of memory. So obviously this is slower than having a flat memory map like the 68K processor has, but it is a good way to get early 8-bit CPUs to access more than 64K of RAM. How does it select between these this upper page? Well, the Z80 CPU is what we call an I/O mapped processor. Some CPUs like the 6502 and the 68K are entirely memory mapped. So when you have a peripheral, like say your keyboard, right? When you type a key on your keyboard, one of those types of CPUs, it would write that value into the memory map somewhere. It wouldn't actually be memory, but the device would be accessed in the same way as accessing the RAM. In I/O mapped CPUs, it uses what they call it a separate bus, a separate I/O bus. It's not really separate. It shares the same data and address lines that it uses to access RAM. But there's another line that tells the rest of the hardware whether it's an I/O cycle, i.e. accessing a peripheral, or a memory cycle, i.e. accessing memory. And on the Z80, there isn't really any practical difference, I mean, at this level of the discussion, between I/O cycles and memory cycles, other than one asserts the memory cycle control line on the CPU, and the other one asserts the I/O cycle line on the CPU. And there are only 256 I/O ports. They only use the lower 8 address lines to select the I/O port, so you can't have as many I/O locations as you have memory locations. So in order to access a full 512K on this RAM chip, the way the Model II does it is at I/O port FF there is a latch, and it's an 8-bit location, but as far as the memory page selection, it only uses the lower 4 bits of that I/O port, and you write a number to that I/O port between 0 and 15, and it latches those 4 bits and gives us our 4 additional address lines, A15 through A18, to access a total of 512K of RAM. Note that we're dealing with 32K pages here, which is A0 through A14. A15, even though the CPU address is 64K, A15 gets used by the bank decoding circuitry, and additional logic that we're going to add on here handles it. It doesn't hook, the bus doesn't hook directly to A15 on the RAM, like you might expect. So the original Model II memory card uses discrete TTL logic to do all of the I/O port and memory address decoding, and that takes a lot of integrated circuits. It's part of what makes that card so big. However, we can simplify things a little bit using an early form of programmable logic called the GAL. GAL is just basically a reprogrammable PAL, programmable array logic. This is a GAL 22V10, both of these are, which is a little more advanced than some of the GALs that look the same are that you'll come across. It has latches inside of it that can be programmed, unlike, as far as I know, unlike the some of the slightly earlier GALs like the 20V8 and the 16V8. So the 22V10 is a little bit special. It's a little bit different. It's a little bit more powerful. That's why we're going to use it, because we need that latching functionality. They don't cost very much more than the old GALs either, and these are still in production, unlike some of the older GALs, so that's good. So basically what we do is we write a series of logic equations that perform the same function as all of this discrete logic did in the original card, but then we compile it into a fuse map, and we burn that fuse map into the GAL, and then the GAL acts like all of this discrete logic did, we put some shit on some input pins and some shit comes out of some output pins based on the equations that we program into it. So let's examine how we might do that. We're going to use two 22V10s because one just doesn't have quite enough pins on it. We're going to use one for I/O port decoding, and we're going to use another one for memory decoding and for the latching of those upper 4 address bits onto the RAM chip. So let's talk about the I/O port decoding gal first. We'll hook several signals to the Model 2 bus. Now note, all of the original Model 2 peripheral cards are fully buffered. They'll have, well, they don't use LS245s because the Model 2 bus is inverted. They'll use like a LS640, I think it is the inverting bus transceiver. Yeah, 74 LS640, I think. I don't have any of those in my box. I guess if I'm going to be hacking on Model 2 hardware, I probably ought to fill a drawer with them. Anyway, I'm losing my train of thought. What was I talking about? Oh yes, I/O port decoding logic. We have to talk a little bit more about the Model 2 memory map as well. Remember I was talking about that I/O port FF that allows us to select those upper 4 address lines? Well, there's also another bit of that I/O port that's used by the memory card. The most significant bit, bit 7, when you turn that bit on, it causes the upper 2K of this upper segment to be mapped out. It disappears from the RAM card. If you try to read or write to that 2K when that bit 7 of I/O port FF is enabled, it acts like nothing's there. And the reason for that is the video and keyboard card also watches that I/O port, and when it gets enabled, it maps the 2K video RAM into this upper space right here. That allows us to read and write directly to the video RAM. And then when that bit is disabled, the video and keyboard card sees that and unmaps its video RAM, and the RAM card maps that 2K back in. So our gal is going to have to deal with that. In addition, when we select page 0, when we write a 0 to the low 4 bits of I/O port FF, like we wanted to map page 0 into the upper 32K as well as the lower 32K, what it actually does is completely unmaps that upper 32K. When we select page 0 in that I/O port and try to access any of that upper 32K, the memory card just acts like there's nothing there. It doesn't do anything with it. The reason for that is that the M68K CPU cards for running Xenix, they are able to map some of the 68K RAM, the 68,000 CPU's RAM. It has a separate RAM cards from the Z80 part of the machine. It's kind of interesting multiprocessing that goes on in those Model 16s, but it's able to map some of its RAM into the Z80 address space, into that upper 32K, and that's how it communicates with the Z80 when you're running 68,000 software, and the Z80 is just acting like an I/O controller. So that's another thing, the 0 page. So right now, our I/O port decoding gal has to keep track of the video RAM being enabled. It has to keep track of the 0 page being mapped into the upper segment. And in addition, there's a separate I/O port. I don't remember which one it is off the top of my head. It might be 9E. It's detailed in the CPU section of the technical manual. I'm not going to move all of my shit and look it up, but in any case, when the least significant bit 0 of that I/O port is enabled, it maps the boot ROM into. So I may be full of shit about this. We can change it in the with the GAL equations if I'm wrong about this. I'll have to look it up when I'm programming the GALs anyway. But I think it maps a 4K ROM segment in at the lowest part of the memory map. All right, but the boot ROM is actually only 2K, so my supposition is that it only actually maps in that lower 2K, and the 2K right above that probably is empty whenever you try to access it. But I think they left space in there to be able to, you know, upgrade the ROM, even though they never did. I may be full of shit about that. I'll have to look it up before we actually write the equations for this. So we have to be able to map that ROM in and out. And in addition, when the system is reset, whether when you flip the switch on the front or whether when you first power it on and the power on reset circuit generates a reset signal to get everything into a known state before the machine starts executing, the memory bank stuff has to be reset, and the 4K of this ROM area has to be mapped in, because the Z80 always starts executing at address 0. So this ROM has to be mapped in when the CPU is reset and starts executing. So it'll start executing this boot ROM, okay, and the boot ROM copies some of itself into RAM somewhere and then writes to that whatever it is, E9 page or whatever it was, and disables itself and returns this 32K lower bank 0 to its full size. So we also have to monitor whether the ROM is enabled, and we have to keep track of the reset signal. Right? Here's how I propose that we wire up the I/O port decoding GAL. Okay. It'll have to watch bus address lines 0 through 7. It doesn't have to watch anything higher than that because I/O decoding only happens with those lower 7 or lower 8 address lines. And of note, I was about to say before, but I lost my train of thought and started talking about that other stuff. All of the existing Model II cards are fully buffered. That means that they'll have like line drivers on the data lines, and I think probably on the address lines as well. Any of the signals that the peripheral card has to access off the bus will be buffered on the card, because according to the documentation, it's bad practice to let a card appear to be more than one TTL load to the rest of the bus. However, these GALs are CMOS logic. Well, internally they're CMOS logic, which is far lower power than this old TTL logic. And in addition, this is a CMOS RAM chip. Now, just of note, the logic levels, the voltages that constitute ones and zeros are a little bit different between TTL logic, which is the older style of logic that the rest of the Model II is built with, and CMOS logic, which is what newer stuff's generally built with. But these particular chips, this RAM chip, they all operate on TTL voltage levels, even though internally they are CMOS chips. So we don't have to take into account any special design considerations. It's just worth noting that since they are CMOS chips internally, they don't draw nearly as much power as TTL logic. Conversely, they also can't source as much power. So that may be an issue that we'll talk about that issue later. But in any case, since the CMOS logic is lower power than the TTL logic that the rest of the machine is made out of, I don't think we'll have to buffer anything. A lot of stuff goes through these GALs before it gets to the RAM anyway, and I don't think that these three chips together are going to constitute enough of a load to necessitate buffering everything on the bus. We are going to buffer the data lines anyway with LSTTL logic, but we'll talk about that later. Alright, the I/O port decoding, getting back to that. We have to take into account the first 8 address lines, so we can decode I/O port FF or E9 or whichever one it is that maps the ROM in and out. We also have to take those lower 4 data bits into account, because that's the page that's getting mapped into that upper 32K segment. But we have to take those into account because we want to produce a signal that tells the memory decoding logic down here when that 0 page has been mapped into upper memory, in which case it doesn't want to activate the RAM when anything tries to access any of that upper segment. Alright, so yeah, we'll watch the write line and the I/O cycle line. We also have to have the clock line because we're going to be decoding the I/O port writes to FF and E9 or whatever it is, and using those to set some latches for whether or not the ROM is enabled, that lower 2 or 4K, whichever it was, whether or not that upper 2K of VRAM is enabled, whether or not the 0 page is not mapped into the high 32K segment, and we'll also produce a signal to tell the memory decoding gal when it needs to latch those upper 4 bits onto its output, because it'll be generating those address select lines for those upper memory pages on the RAM, right? So that's 4 output signals and 8, 12, 13, 14, 15, 16, 17 input signals. That almost takes care of the 22 lines on the I/O port decoding gal, but we've still got a couple left, like if we have to change a little something. So anyway, let's go down to the memory decoding gal now. It's not quite as complicated. We have to keep track of bus address lines 11 through 15. That allows us to tell which 2K segment is trying to be accessed, because that 4K ROM segment down at the bottom, that's a multiple of 2K. That upper 2K VRAM segment, we have to be able to tell when they're being accessed so that we can not have the RAM respond when those other things are enabled that come out of this I/O port decoding gal up here, right? We have to keep those first 4 data lines in mind. We have to take them in because when we get this page latch signal from this I/O port decoding gal up here, it needs to latch the value of these 4 bits onto these 4 bits of output here to be passed on to the RAM chip. Alright, we also have to keep track of the memory cycle line off of the bus, because that helps us, in combination with these other 3 lines that come from this gal up here, in combination with that memory cycle signal, will allow us to select when to actually enable the RAM chip or not. Right? So from there, we can go into the actual RAM. Here it is. Address lines 0 through 14 hook straight to the bus. Nothing funny there. Address lines 15 through 18 are latched by the memory decoding gal down here. They hook onto the outputs of it. The data lines 0 through 7, I've got them drawn here hooking straight to the Model II bus, but I don't think we want to actually do that, but it's a trivial matter to change that. We'll talk about that in a second. The read lines and the write lines hook directly to the write enable and the output enable lines on the RAM, and the chip enable on the RAM hooks up to the RAM enable signal that comes out of this memory decoding gal down here. So that's the entire memory interface right there. However, like we were saying, that is a CMOS RAM, so it's not going to be able, it's probably not going to be able to source enough current to drive some gnarly old shitty old card with a bunch of like high-powered like 7400 series logic on it. that's like sinking a whole crap ton of power out of the thing, right? So we are going to buffer those data lines with an LS245 bus transceiver. And the way we can do that is we can hook the NOT G line of that transceiver straight up to the RAM enable line, and we can hook the direction line straight up to the read or write line. It doesn't really matter which. It just depends on which way is most convenient with the PC board layout to run the lines through the chip, right? So note though that the Model 2 bus is inverted. Some of the implementations of RAM cards that I've seen, schematics up for the Model 2, invert all of those address and data signals while they're being buffered by the bus transceivers. But that doesn't make any practical difference for the purposes of this implementation. It doesn't matter whether the data lines on the RAM are active low or active high. It's basically just garbage in, garbage out. You write a low signal into the RAM, you ask for whatever the contents of that location is back, you get a low signal back out. You know what I'm saying? And we can write the logic equations in the gals in such a way that they operate properly with that inverted logic on the bus, and we won't need to invert all these signals with a bunch of extra chips, I don't think. So that's my thought for the 512K memory card for the Model 2. That'll be it right there. Assuming I didn't miss anything, 4 chips will more than replace, 8 times replace this big board right here. What do you guys think? Am I missing something really obvious here? What do you reckon? Thanks for joining me. Let's make a thingaroo down in the comment or do, telling me what your opinion is of all this crazy garbage. Alright, bye.